Hi, this is lecture 6, and today we'll be talking about atomic spectra and the Bohr model. Before we get too far into that though, I wanted to share something that my mom shared with me over the weekend that I thought was fun. This is from our genealogy here. And you'll notice that I have some ancestors that are kings and queens of Asgard and some other descendants that lived in Asgard. And if you know your Norse mythology or have been watching the Marvel movies, you'll know that Asgard is the home to the Norse gods, such as Thor and Odin. So kind of fun. I don't actually know where Asgard is in real life, what the city or region even is, but that's fun. All right, let's start by talking about white light. So if you don't know this already, if you take white light and you pass it through a prism, which is just basically a triangular piece of crystal or quartz, that prism will spread out the light passing through it and create a spectrum of color, a rainbow. Then this spectrum is continuous. It starts from the red and goes to the violet through that Roy G. Biv that we talked about before, and it covers all the colors. But it turns out if you look at the sun looks like it's emitting all the colors, but it's actually not. It does emit red, orange, yellow, green, blue, indigo, and violet, but there are discrete wavelengths of light that it's not emitting. It's just got these wavelengths that are blacked out for some reason. And these lines are what are known as Fraunhofer lines, because Josef von Fraunhofer, who was a Bavarian scientist, studied these, and he identified 570 or so dark lines in the emission spectrum of the sun, just wavelengths that were, for whatever reason, missing. Nobody really knew what was going on or where these black lines were coming from, though they did get some evidence about a half a century later when Bunsen came onto the scene. So Bunsen was a German chemist, Robert Wilhelm Eberhard Bunsen, and he's also the guy that developed the Bunsen burner that every scientist uses at some point in their career. And he used the Bunsen burner to heat different materials up, including gases. And he noticed that when he heated different materials up, or different gases, that they emitted different lines from one another, and those lines seem to be at the same places as these black lines corresponding to sunlight. And so we don't really know at this point, at 1859, why this is occurring, but we do know that it's correlated with different materials. Now let me pause here to say that I've gotten a lot of questions about the history that we've covered and how much of it you need to know. You don't need to know individuals' names or dates, but you should be able to, if I give you an experiment, one of these important experiments, explain to me what the experiment was, what the actual results they saw were. So for example, Fraunhofer's results were these black lines, and then you should be able to give me the interpretation of that result. So what does it mean? And I haven't given you the interpretation of this experiment yet, but by the end of this lecture, you'll be able to get it. So Bunsen, basically his results looked like this. When he heated hydrogen gas, he got 4 wavelengths of light being emitted off the hydrogen gas. And 4 very specific wavelengths. When he heated up helium, he got different wavelengths. And he saw 1, 2, 3, 4, 5, 6 wavelengths coming off of helium. So now you can see it's getting a little more complex than the hydrogen. When he took neon and heated it up, he actually got a lot of different wavelengths of light. It's a much more complex spectrum. Now the takeaway from Bunsen's experiments were that each atom emitted specific wavelengths of light, or each element emits specific wavelengths of light. And those wavelengths are generally unique to each element. Some elements do actually happen to have wavelengths that overlap with each other, but that's generally coincidental. And the real point is that each element has a fingerprint, an emission fingerprint that is unique to it, and that isn't shared by any other element. And so what's interesting is with how this relates to the Fraunhofer lines is that, so if you heat a gas up and pass its light through a prism, you get distinct bands. But if you take white light and pass it through this material when it's cold, you actually block out parts of the white light. You have black lines that are in the exact same places at the exact same wavelengths as you get in the emission spectrum of that material when you heat it up. So matter emits and absorbs light at the exact same frequencies or wavelengths. So it emits light when it's hot, it absorbs light when it's cold. And so if we take the spectrum for hydrogen, helium, and neon here, you'll notice that they each have dark lines in their absorption spectrum down here in the same place where they have bright lines in their emission spectrum. So emission comes from hot material, and your emission spectrum are individual lines. Your absorption spectrum is measured relative to white light, and it's the black lines that are absorbed. So your absorption has black lines, your emission has colored lines. Let's see how you're doing with that idea. Which of the line spectra below is an emission spectrum? Go ahead and pause the video right now and try and figure it out. All right, the answer is B. B is the emission spectrum because it's emitting these different wavelengths of light. And A, of course, is the absorption spectrum. So just to review what we've covered so far, if you have white light, it goes through a prism, gets spread out, you have a continuous spectrum of colors. If you heat a gas up, it will emit emission lines, which will show up as just colored lines at different wavelengths. If you combine these two experiments, sort of, if you take white light, send it through a cold gas, that cold gas will absorb lines. And so you'll get black lines in the white light spectrum. Let's try this now. Let's ask another question. This is a little more challenging than the last one, but let's try and match this emission spectrum with the absorption spectrum of the same element. Go ahead and pause the video right now and see if you can do this. All right, so what we said was the emission and absorption spectrum match each other. Or another way of saying that is that they're opposites of each other. The emission spectrum is all colored lines. The absorption spectrum is all black lines. So to match these, all we have to do is look at where these lines are and look at the spectrum that has black lines in the same place. If we start with D, we'll notice there are no black lines down here where there are clearly black lines in our emission spectrum. So it's not that one. If we look at A, it's got a bunch of things blacked out right here, only about a single line or two with emission right here. So it's not A. Now B and C, they both have a lot of lines in fairly similar places. B has some more density than C. So for example, B has a lot of dark lines right here that just aren't in that emission spectrum. So it's not B either. So it's got to be C because it's got all these lines in exactly the right places. All right, so let's talk about these lines now, though, and get into where they're coming from. So scientists started by studying hydrogen because it had the simplest emission spectrum. There's only these 4 lines in the visible spectrum. And then it actually has a lot of lines in the IR and UV region. So for example, this 397 nanometer line is in the UV region. But it only had 4 that the scientists could see right away. And these 4 visible lines are what are known as the Balmer series. And they're known as the Balmer series because Johann Balmer was the first one to really make a breakthrough with these wavelengths. And what he discovered was that they were related somewhat to integers or differences in integers. So in his equation here, we have 1 over lambda being proportional to 1 over 1 integer squared minus 1 over a second integer squared, right? So integers would be 1, 2, 3, 4. And that's actually as far as he got. He didn't get much farther. Rydberg came along a couple years later and said, hey, Balmer, why don't you throw a constant in front of that and make it just the whole equation? And so what Rydberg did was he was able to calculate the actual locations of the Balmer series lines using this equation, where it related the wavelengths that appeared to individual integers and a constant, which we call the Rydberg constant. And this equation actually is able to predict not only the Balmer series, but all the wavelengths seen in the UV and in the IR and everywhere. So in this equation, you have N1 and N2 as integer values, and they can't equal each other. So N2 is always bigger than N1 in this specific equation. And then we have the Rydberg constant R, which is just this value. And it's in inverse meters. The reason for that is because over here we're doing 1 over the wavelength. The wavelength is in meters. So Rydberg got us to the point where he could predict all of the wavelengths, but he couldn't actually explain where these lines were actually coming from. And that's where a young man named Niels Bohr came into play. So Niels Bohr used quantum mechanics to explain where these line spectra are coming from. And just a reminder, quantum mechanics, or quanta, it just means a specific amount. So if it's quantized, if anything is quantized, that means it exists only in specific quantities. Now, this is big news for the science community. Not everyone was a fan. For example, Homer Simpson wasn't a fan, and actually Einstein wasn't a fan, but now I ruined my segue.
Instead, we bring you the boring world of Niels Bohr.
I like how the dog comes up and licks it. I'll deliver that better in lecture. Okay, but let's talk about the Bohr model and what's being quantized. So what Bohr said was that the orbitals, or the distance at which electrons orbit the nucleus, also known as the orbitals, are quantized, meaning that the electron can only orbit at specific distances. And what that means with those specific distances is that it also has specific quantized angular momentum and energy. Now, you don't need to know a ton about angular momentum at this point, other than it's a way of describing the electron moving with momentum that's angular or rounded. So it's the electron spinning around the nucleus. And energy means that at each of these orbitals, the electron would have a different energy. Now, if you'll remember n, our principal quantum number, which is just an integer value, right? All these n's we see everywhere are just integers. N can be used to describe the different orbitals here. And it also thus controls the energy level, where the lowest energy is at n equals 1. So there's no n equals 0. The electron's lowest orbital, or lowest energy it can be at, is n equals 1. And then if it gains energy, it can be promoted to a higher orbital. And when it's promoted to a higher orbital, that's called an excited state. So when it's relaxed, it doesn't have any extra energy, it's at its ground state. When it gets extra energy, it gets up to an excited state. We can use the Bohr model to explain why matter absorbs and emits light in specific wavelengths. So when an electron absorbs a photon, it jumps from one energy level to another. And since these different energy levels have quantized energy, meaning they have a specific energy associated with them, then you have to absorb the specific energy to jump from one energy level to another. So this change in energy is described right here in math terms. So this triangle right here is what's called delta. That's the Greek letter delta. And in math, it means change. And so the change in E, which is energy of the electron, is equal to the energy of the photon that's absorbed, h nu. And so this electron can jump to any orbital it wants, as long as it can absorb the energy difference between those two orbitals. So whatever the difference in the energy of those orbitals is. So when electrons absorb a photon of light, they get excited to a higher orbital. But then where does the emission come from? Well, so electrons can actually get to these excited orbitals through heat too. If you heat up something, it can get it up there. But then once the electrons are up here, they actually have some probability of falling back down. And when they fall back down, they then have to get rid of that extra energy, and they do that by emitting a photon of light. So when they change from a higher orbital to a lower, they emit a photon. When they go from a lower orbital to a higher, they have to gain a photon. Now, electrons can't exist between levels. So the photon energy has to be exactly the difference between the two orbital levels. And that's why you get really specific bands. And so another way of saying that mathematically is the change in the electronic, or the energy of the electron, is equal to the energy of the final orbital minus the energy equal to the initial orbital. And that is equal, of course, to some h nu, which corresponds to some photon out there of that same energy. But this orbital idea gives us these sharp lines in the emission and absorption spectrum. Now, Bohr went crazy with physics and derived an equation that would describe the energy of specific orbitals. And now, while this equation is really useful, it actually comes with two really big caveats. The first is that it only works for a hydrogen atom. So it only works for an atom of hydrogen with a single proton in it. The second big caveat is it only works when that proton has a single electron in it, which means that this equation actually doesn't work for the vast majority of atoms. However, it does give us some really good insights into the way electrons behave, and so we actually still use it for some really simple modeling. Now, in this equation, you have E is the energy, Z is the atomic number, E is the elemental charge in the electron, Me is the mass of the electron. You have 8 pi epsilon naught squared. That's all just a proportionality constant. It's got Planck's constant, and it's got this principal quantum number in here. Now, because this all works only for the hydrogen atom with one proton and one electron, it can actually be simplified way down. And so we usually look at this equation in this form of E equals negative hc. So h is Planck's constant, c is the speed of light, RH is Rydberg's constant, times 1 over the principal quantum number squared. And so as you can tell, that's a lot more elegant, a lot easier to use than this big giant equation. So we like it a lot. But what is this equation describing? Well, it's describing the energy of specific orbitals, but we usually care about the difference in energy. So let's look at this. So we've said that absorption and emission spectra result from electronic transitions, right? So from an electron going from this ground level to the second level, or the ground level to the third, or maybe from this sixth level down to the third, or maybe the fifth level down to the second. So it's the electron jumping around is where we get this color phenomenon. So the change in energy that an electron feels, like we said, is equal to the energy of the final orbital minus the energy of the initial, and that's equal to some photonic energy. Well, we just found the actual energy of specific orbitals, and that's actually listed here on the left, the energy of each orbital. So we can make substitutions in this equation. So we can say delta E equals all of this, where we have that the principal quantum number of the final orbital, the principal quantum number of the initial. And if you know some math, you know that a lot of this will factor out. And so you'll get delta E equals negative hc Rydberg's constant times 1 over the final quantum number squared minus 1 over the initial quantum number squared. and that's equal to h nu. Okay, so now we know how to calculate the energy from moving from one orbital to the next. So going from orbital 1 to 2, or from 3 to 2, from 5 to 4, etc. So let's try and get this solid in our brains. So if an electron moves from the n equals 5, that's right here, orbital, to the n equals 3 energy level, does it absorb or emit energy? Okay, so it's going from 5 to 3. Well, let's start by figuring out what the sign of delta E is. So let's do this by playing around with this delta E equation. So our change in energy is equal to negative times 1 over the final quantum number, right? And so here we're jumping to the n equals 3 state, so it'd be 1 over 3 squared minus 1 over the initial state. So we're jumping from n equals 5 to n equals 3, so it'd be 5 and 3 on the bottom. Those are squared. That'd be equal to negative 1 over 9 minus 1 over 25. 1 over 9 is a larger number than 1 over 25, so the stuff inside parentheses is going to be positive, but it's got a negative sign outside, so this will all be equal to a negative number. So your change in energy here, the point that I'm getting at is your change in energy will be negative. Does that mean that the electron is absorbing energy or emitting it? Well, if it's got negative energy, so if its change is negative, it's not gaining, it's not absorbing, so it has to be emitting. So anytime you're going from a higher level to a lower, you are emitting. When you're going from a lower to a higher, you are absorbing or gaining energy. It takes positive energy to get up there. So this leads us into the sign conventions for these orbitals. As we're talking about the energy of these different orbitals as being negative energy. And this is because of the notion that we want zero energy to equal a free electron. A zero energy would, or at zero energy, the electron has popped off. So your energy levels are negative, but they can be thought of kind of like the negative balance on your credit card, or the amount you owe on your mortgage, right? This is the amount of energy you have to give or pay off to free the electron. So the farther down the lower orbital you get, the more it takes to get your electron off. So adding energy is absorbing a photon, gets you closer to zero, gets you higher in energy levels. So you're increasing your principal quantum number there. And so you get a positive change in energy. You're getting close to zero. If you're losing energy, then you're emitting a photon, you're getting more negative. So the change is negative, right? You're getting farther from zero, you're getting farther into that hole, taking out more and more debt. All right, let's practice with some of these ideas that we've learned. The blue line in the hydrogen emission spectrum shows up at 434 nanometers. Now, like we've said, emission is the electron relaxing from a higher level orbital to a lower level orbital, right? So it's getting negative energy as it goes down, so it's emitting light. So what we want to know, though, is which energy levels are specifically being involved. So to figure this out, we're going to have to use Rydberg's equation. So Rydberg's equation, right, RH times 1 over the final quantum number squared minus 1 over the initial quantum number squared is equal to 1 over lambda. Now to figure this out, we're actually going to try and isolate our quantum numbers here. So we're going to divide the Rydberg constant over it. So we're going to get this whole big thing in parentheses equal to 1 over the Rydberg constant times lambda. And the Rydberg constant, I didn't give it elsewhere on the slide, but it's right here. It's also on your equation sheet for exams, and it's in the front of your textbook. And we'll times that by our wavelength. Notice here that we changed to meters instead of nanometers, and that's just because Rydberg's constant is given in per meters. But when we do this math, we get 0.210. Now you notice there's no units on that, and that's because this is equal to our initial parentheses, and I'll simplify that down now. Both our quantum numbers are unitless, and so our answer should be unitless. Now you might think, oh man, Dr. Mortenson's about to teach us some crazy trick for solving this. Well, I'm actually not. You could try and simplify this, but it's actually not very easy, and it gets pretty ugly pretty fast if you try and simplify it. So what we're actually going to do is we're just going to guess at these values. We know they have to be whole numbers that are greater than 0. And that makes it a little easier. But what I'm going to do is I'm just going to try 1 and 2 first. So I've plugged in 1 for the final quantum number and 2 for the initial. When I work that math out, I get 0.75. That's not 0.210, so we know it's wrong. We'll try another set of values. We'll try 1 and 3. Well, oh, that got us a bigger number. Now we're at 0.889. We're trying to get to 0.210. So we know those numbers are wrong. All right, so let's try 2 and 3. You'll notice I'm being somewhat systematic about this, but at the same time still just kind of guessing. I'm just trying to guess at numbers where the math will result in 0.210. You'll notice if I use 2 and 3, didn't work. Did get me to a much smaller number though, 0.139. So now let's stick with 2 for a while, and we will play with 3. We'll change that 3 to a 4. Got me a little bit closer, 0.188. Still not quite there. So let's try 5. Okay. So if I do 1 over 2 squared minus 1 over 5 squared, I get the value of 0.210 we're looking for. Now at this point, some of you are like, oh, that's brilliant. And then some of you are thinking, he lost me 5 minutes ago. So let's talk about, or let's remind ourselves what we're saying. What we're looking for is the levels that the electron is relaxing between. So we knew it was starting at a higher energy level, dropping to a lower. We knew that because it's emission. And to get emission, you have to drop from a higher energy to a lower energy. We knew we could figure out which levels using Rydberg constant because we knew which wavelength of light we were seeing. And so just now we figured out that electrons relax from n equals 5 to n equals 2 by releasing a photon with a wavelength of 434 nanometers. And we can then use that to figure out the actual change in energy in joules. So let's see how you're doing with this idea. For which transition would a hydrogen atom need to absorb a photon of the highest energy? Now I've got our equation here for energy down here. It might be helpful for some of you to see this, but go ahead and pause the video and figure this out. Okay, how to think about this. First, let's look at the data. We're trying to figure out which transition would need to absorb a photon of the highest energy. Well, I can tell right away that it's not going to be E. The way I can tell that is it has n equals 0. N equals 0 is not a state. It starts at n equals 1 and works its way up. So it's not that one either. So let's just start at the top of the list now. N equals 5 to n equals 1, n equals 4 to n equals 2. All right, I know it's not either of those. Why? Because the question is saying absorbing a photon. These are going from a high energy level to a low. Their change in energy would be negative. And so they're not absorbing energy, they're emitting photons. So now it has to be one of these two. Now the idea here is to figure out which is a bigger jump. Is 2 to 4 a bigger jump or 1 to 5? And just looking at those, you can figure out that 1 to 5 is a bigger jump, but it could be a more complicated question like 3 to 6 or 4 to 8, in which case you'd actually have to plug the numbers into this equation right here, figure out which one is bigger. But since 1 to 5 is a difference of 4 and 2 to 4 is a difference of 2, we can pretty safely say that D is the biggest transition. So in that, the electron got excited from this n equals 1 state up to the n equals 5 state. And you can see from this diagram, that's a lot bigger than from 2 to 4, which is just this little region. All right, let's try another problem. This one's a little more tricky and involves a little more understanding. Which transition for the hydrogen atom will emit a photon of the shortest wavelength? Go ahead and pause the video and try and figure it out. All right, so we're looking at emission, which means that our electron is losing energy. So if it was absorbing, it would go from a low energy state to a higher one. But it's emitting energy, meaning it's losing energy in the form of light. So it's going from a high energy state to a lower. So it's going from a higher number to a lower. These first two are going from a lower number to a higher, so it's not those. These last two are going from a higher number to a lower, so it could be one of them. Now we got to figure out which is different. Well, 6 to 5 is a smaller difference than 4 to 2. So the answer is this one. And the shortest wavelength, so I guess I didn't make this clear, why we needed the shortest wavelength is because we're looking for the higher energy transmission, or that's how I picked the larger gap. So if you remember, shorter wavelengths correspond to higher energy. So photons with shorter energy have a higher frequency, higher energy. They're going to then result from the largest drops in energy of the electron. So the electron giving up the most energy. And that's why I went with the bigger transition. So if I asked which emitted a photon of the longest wavelength, then it would be, of course, C. And another thing to keep in mind with these, so I give a lot of this in terms of math. I know that's hard for some people, but if you just think that energy changes become bigger for lower changes of n, so if I'm going from n equals 1 to n equals 2, that's always a lot bigger than n equals 2 to n equals 3, and that's bigger than n equals 3 to n equals 4. So if you can remember that it takes more energy on the lower quantum number transitions than the higher, that will help you. So all of these emissions and absorptions are just from electronic transitions. And like I was just trying to make the point on the last page, the distance between these different orbitals gets smaller as n increases. And if you remember, that's because in the equation for calculating the energy of these, we have 1 over n squared. So as n gets bigger, 1 over n squared gets smaller and smaller, right? And the difference between those really small numbers gets smaller and smaller as well. And so you get the biggest transition when interacting with low quantum numbers. Now let me ask you a tricky question, see if you can figure it out. If the Balmer series, which is the spectra for hydrogen in the visible region, corresponds to transitions down to the n equals 2 state, what do the Lyman series correspond to, or what region are they in? Are they UV or IR? So the Lyman transitions, we haven't talked about those, but they're specifically the transitions in hydrogen down to the n equals 1 state. So from n equals 2, 3, 4, 5, 6, etc. to n equals 1. And I want you to think about this. Are they higher in energy or lower in energy than the Balmer series? Well, this transition is denoted with a much larger line, so they're a higher energy transition. Now, is UV or IR higher in energy? Well, ultraviolet has shorter wavelengths than violet. Infrared has longer wavelengths than red. Shorter wavelengths is higher energy, and so it's going to have to be the UV region because it has to be higher in energy than the series described by Balmer, where we're going to n equals 2. So because we're going to n equals 1, we're getting a bigger transition, higher energy, shorter wavelength, UV region. So that's it for most of the information that you need to know. So let's just talk about some fun things now. So if you see something that's glowing yellow, so like a light bulb, it's actually giving off light of multiple colors. So that's why in a room you can have a yellow light bulb but still see the color blue. because the light bulb is emitting it. It's just emitting more yellow than red and green, etc. And so it looks yellow to our eyes. But the opposite is kind of true with absorption. When you see something that's green in the sunlight, like grass, it's actually reflecting the green. It's not interacting with the green. It's actually usually absorbing the other colors, like red and blue. It's absorbing those more strongly than it's absorbing green. And so the object is taking in those other colors. So for example, the chlorophyll that gives plants their green color that you learn about all the time in biology, the chlorophyll actually absorbs blue and red wavelengths and doesn't interact with green. And so we see the green because it bounces off, but the green and red is being absorbed there by the plant, and it's using the it's using the blue and red for photosynthesis. And as the weather changes, as it gets colder and the daylight shortens, your plant stops producing so much chlorophyll. And so as the chlorophyll amount drops, there's other pigments in there that are reflecting yellow and red. And now nothing is absorbing that red. The chlorophyll is not absorbing it. And so it actually starts bouncing back at us more strongly. Pretty interesting. All right, that's it for today. Let me know if you have any questions.